Welcome. In this session on linear data analysis, we'll introduce some definitions that we'll use as we explore vector spaces. We'll begin the way most mathematics texts begin, which is an abstract definition. And this abstract definition is basically a way to both constrain the ordinary interpretation that a computer scientist would have and to allow for certain extensions that mathematicians like. So they begin by saying this starts with a field. And of course, we always wonder, oh no, do I have to learn about a field? The answer is no, you don't need to learn about a field, because what they usually mean is the real numbers. Now they might possibly mean complex numbers, which are usually written as z, or they might mean rational numbers, which are written as q, but in our case, we'll think of them as real numbers. And then they have a set of vectors, and this is where the real action is happening, and we'll represent that as the double-barreled V. And then they have two operators, and we'll say sometimes these are separate axioms. We'll put them as part of the definition of the operators, two operators with closure. And these are multiplication. So the first one is that if you have a constant that is in your field and you have a vector in your set of vectors, then the product of the constant and the vector are also in the set of vectors, and you have addition. And addition is that if you have u in your set and you have v in your set, then u plus v is in the set. And I'll note that there are 8 axioms. Okay, and usually, now I've seen them vary from 6 to 8 depending upon exactly how things are defined and how they interact with the operator definitions, but it's usually 8 axioms. And for this, I will refer you to texts that will go through all of the axioms. And some of the exercises are really worthwhile going through to verify that if you're given a set, that it satisfies all these axioms. Now, we're computer scientists, so these abstract definitions we appreciate them. What we need to do is implement them. So our interpretation, and here I mean it in the same sense that we mean it in logic, which is we're going to drive this down very carefully. And what I mean is that for any u and v that are in the set and any a and b that are real numbers, that if I take a times u plus b times v, that is in the set. And what this carries with it is these 8 axioms. So this manages, we'll say, this manages distribution. For example, that if you just multiply, so that means that a times u plus v equals a u plus a v, and commutative. So we naturally will realize that it'll handle commutative, and so that would be, for example, that u plus v equals v plus u, and so on. And this rule will capture everything that we need. So this is important. And important is that we always have the 0 vector has to be in the set. In fact, the smallest possible vector space you can get is just the 0 vector, and it will satisfy everything. So if you want to learn more about this, I would refer you to the excellent text on linear algebra by Gilbert Strang, who's probably the best teacher of linear algebra on the planet. And I would refer you to specifically to Strang's 5th edition. And I would suggest that you look at section 3.1, exercise 10. And exercise 10 will give you examples where you can verify whether or not it satisfies this rule, and if it doesn't satisfy this rule, you can drive down and you can figure out which of those 8 axioms is not being satisfied. So let's think now about what's the simplest example, and that is a coordinate space. And this is a fancy name for what you probably think of as an ordinary vector space. So this is also called a Euclidean space, and it's also called real space. And I'll just say ... because there are lots of names for it. And we write this as real numbers to the power m, and what we mean is that this coordinate space is every vector that has m entries that are real numbers no matter what they are. Now, let's consider a matrix that's in a space, and suppose the matrix has m rows and n columns. And you can ask yourself, does it satisfy this equation? That is, if I give you 2 matrices, think of it as capital U and capital V, right? So let's write that down, capital U and capital V. And if I multiply matrix U by value A, and I multiply matrix V by value B, and I add them, is that a matrix that has real entries with m rows and n columns? And the answer is yes. So things that what we normally think of as vectors live in vector spaces, but vector spaces are much more general, and they include things that you might not naturally think of as being a vector space. This is why sometimes we have to go all the way back to this abstract definition and check these 8 axioms, because sometimes a vector space will pop up in a surprising context, and we can verify now that we understand whether something is a vector space by, does it follow, is it subject to these and the 8 axioms, or if we want to do a very quick check, does it satisfy our simple equation? When we implement a vector, or when we write computer code for a vector, we have some further restrictions on this abstract idea of a vector space. So what we'll say is that for us, if a vector is in a vector space, then there is a, I'll be specific, a finite integer m such that the vector that we're looking at has m entries and is real. And we'll put this requirement, it might seem, well, why are we doing that? Well, it's because there are infinite dimensional vector spaces, and we won't be exploring these in our work. And there are also ways that you can get vectors with different sizes to follow all these rules, etc. We don't want to look at that. So we usually, and I'll just say, but not always, have a dot product. And a dot product is a special kind of thing called an inner product. What we want is a dot product. And so in a vector space that has a vector u in it and a vector v in that space, we'll say that u dot product with v equals by definition, and we could say that equals that's u1 v1 plus u2 v2 and so on until we've expressed all of the entries, and that is the same as saying that it is the sum as j goes from 1 to m of uj vj. So when we have a dot product, mathematically, that gives us the transpose. And you might think that the transpose is something that's just natural, that it's just there. And it turns out that mathematically what you have to do is we usually define a dot product and then we can define a transpose. And so once we have a dot product, we also have a transpose that we can write this way. And what we have is that u dot v, we can write that as u transpose v. And this formula can get us out of some sticky situations where we're trying to figure out what happens when we add vectors and then take a dot product with something else. When we get into slightly confusing situations that involve the dot product, we can always revert to saying that it's one of these vectors transposed with another. Now, if you look at this, that means that also equals v dot u, and that means that I could write u dot v is u transpose v, and I can also write that as v transpose u. And this equivalence, it doesn't look as though it should be true, but it comes out from this fundamental definition of our dot product. We also usually, and this depends upon a lot of other mathematics, but we usually have the Euclidean norm. And the Euclidean norm is our way of saying distance or length. And we write this with double bars, and that is the square root of the dot product, which is the square root of u transpose v. And then let's write this out in terms you might have seen before, is that is the square root of the sum as j goes from 1 to m of uj squared. So when we refer to the norm of a vector, we'll always put these double bars around it, and what we mean is take the dot product of a vector with itself and take the square root of that scalar number, and that is the norm of the vector.